So first, do you have any questions for the announcement for the course project? Any questions on that? Is that clear enough? Yeah? Still have questions? Okay. So the accelerometer is something you have to build on the data board for lab 14. If you want to move forward with the accelerometer, the only concern here is we won't be able to cover that until the what's the date? Whatever, lab 14 is moving into November. So if you want to use the accelerometer for a project, I can share you share the code with you, because eventually you are not actually coding it up. So if you look at lab 14, which is everyone is going to do it, and if you get into here, there's no programming. It's just a hex file, I believe. No programming required. It's just several like math and general questions about the sensor. Okay. However, I have the code already shared by Dr. Carlson, but he's not trying to let you code it up yourself with the I2C. So if you want to work on the accelerometer project, I can announce it. I can just share the code with you, announcement, so you can look at it. And let me look at the schedule when we are going to cover the accelerometer stuff. I just have to. It's a very important sensor to learn, okay? So that's gonna be here, mid-November. It's right, it's almost the end of the project. So that's why, so yeah, definitely we'll cover a little bit over here, okay? Since we don't have enough time, because we have lab 9 and lab 10, which are pretty much the same lab. You got the signal acquired to the SD card and then eventually play it back. So now I'm almost getting this step-by-step instruction done. So this weekend I will get the lab 10s done. So I already did it. It's not difficult at all. So most of the code is being shared. I'm giving you a template. Depending on your stress level, I can tell from your face. So I will decide like how much I'm gonna provide in a template. So these two are really good projects. So for students who are willing to work on the microphone, ADC, SD card, these are important labs you want to go through. Okay, and then after that, I think we don't have much pressure anymore. So this week lab 8, I'm going to cover that today. Next week lab 9, lab 10 is pretty much the same lab, just a little bit more on lab 10. SD card, microphone, done. Then after that, these two are easy. This is just soldering, a little bit math. I'm gonna just tell you, I'll cover all these in-lab questions during the lectures over here. So be ready to answer those questions and come to the lab, solder it, put it in the oven, like cooking, right? Just think about it as a kitchen, cooking, done, get a board, measure it, have some fun. And this is optional. If you are working on your own project, this is optional. Even though you got a data board, you don't have to measure it and do everything over here. Just for people who are trying to use the accelerometer for their project. So this becomes a track 1, right? If you went through the flyer I sent to you guys yesterday, so you'll see this is track 1, project track 1. You have to do lab 15. Okay, for track 2, which are your custom board and PCB and whatever. Okay. And there's one very good project for the accelerometer, which can involve the speaker and accelerometer, which is called burner alert. Because my wife, a lot of times she forgot to turn on the burner at home, so I get worried about that a lot. And also, about 8 years ago, the first time I moved into my house, I actually just myself, because my families were still somewhere else. So I actually rented out my upstairs for to students, college students in Durango, and one of the guys forgot turning off the burner for like almost once a month, once or twice a month. If you have roommates, you probably know that kind of people. Like, they just forget, they just forget it. So in that case, I worry about that a lot. So I was thinking about how can I get a sensor and alert system in the house so I can receive a text message or something. I thought about so many different ideas. So for example, temperature sensor, but doesn't work. Why? It takes time to cool down, right? It's gonna be hot for a while. whenever someone is leaving the house, the temperature sensor is still high. I mean, who knows it's on or off? You couldn't tell. And I was thinking about the IR camera you put on the top of the burner, so showing like 4 circles, and project it to a monitor in the house. So before you leave the house, you look at the monitor, still red hot, still not working. It's too complicated. Like involving the Wi-Fi signal and just getting a burner alert for like $400. Who's gonna buy it? Doesn't work. So I eventually found out this product, and it's only $80. I mean, the cost is lower than $10. I can tell. Sorry.
You're a robot.
It's been there for a while. Anyway, so this guy, this is a little circle, little plate, and has a PCB, circular PCB inside this little container, and it has a accelerometer inside detecting the angle, and also just attaching to the knob. Okay, so when you turn it, it detects the angle change, and will beep immediately for 3 times, and after that, it takes like another 3 minutes. It's gonna beep again. All right, and after a while, so the third beep will take like 10 minutes, because sometimes when people are doing a slow cook, right, it takes time. So you don't want to always hear the beep every 3 minutes, right? So the third time will be like after 10, 11 minutes. It's not going to 100% solve the problem. Seems like it's too simple, right? It's a very simple system. However, it works. After I bought it and installed it, I've never got any issues in the house for like over, it's almost like 3 to 5 years, I forgot, but at least 3 years. I've never had any issues. It's working. You have a question?
It was more of like just like a product question more than anything, but it was like, because it comes in a 1 pack for $40. I was wondering how much the 4-pack was.
4 packs is 80.
Yeah, 80? Gotcha.
Yeah,
Okay.
yeah. And I was searching on.
And then also my other question was like, I cook a lot, right? And I know that like I turn on the burners, like I'm using the burners for like 5-10 minutes when I'm cooking, right? Is it beeping the entire time that I'm cooking?
It's not bothering at all.
Okay.
It only beeps so at the beginning it beeps, right?
Okay.
Right after you turn it on. And then beeps after the 3 minutes. And then it takes longer. So third time it takes longer for people who are.
Oh, it's got it right there.
Yeah.
Gotcha.
It's programmed in a way that it's not really annoying people. So it's been working. It's really nice. And I was searching online for the company's profiles. There are only 2 people in the company and making $500,000 just by selling this product. So you can imagine if you know how to build systems, PCB design, programming, microcontrollers, you can just start up a company if you want, selling products like this and making a lot more money compared to like just getting a defense sector job like $90,000, which was good but not good anymore after the inflation. Okay. And there's another company selling charge pumps and making a little biology container, like kids can put mud into it and dump like milk and ketchup, and eventually the bacteria it's called geobacteria. You can sample from the river mud, and that geobacteria will grow in that little container and eventually sending out electrons outside of the bacteria's membrane. So you insert the wires into the mud, and eventually it discharges and light up the LED. So the voltage is usually 0.3 millivolts, but the charge pump will boost it to somewhere around like 2 volts. So eventually it blinks the LED. So it's a really interesting educational kits being sold by companies. They have other products, but that one is being sold the best. I don't know, like 200,000 kits being sold to all the schools, high schools and colleges. And they are making like $20 million a year just by selling that little PCB board. So I definitely didn't know how to design what the schematic looks like, but I bought like 40 kits. I was looking at the PCB so simple. I just used my multimeter. I'm not stealing their technology anyway, but I used my multimeter. I probed to the continuity check and was able to find out the schematic. And I drew the schematic and fabricated a PCB. Eventually I plug in all these wires into the mud and it works. So I just don't want to sell it because I know this is their IP. But if I want to use it for my college, for schools, local schools, I can probably give them a credits. If I sell it to these schools, get a permit from that company, so I can just serve my local community by doing that. Not making $20 million, but even though it's $50,000 a month, still good. So just give you some examples, okay? This is a really good example for the projects because they are doing the accelerometer, detecting the angle, and at the same time engaging the speaker. So getting a timer to count, like beep every several minutes. It's a really good project. So if you are doing that, I'm going to require you to manufacture that PCB as part of it. But no pressure, okay? Just get it work on the breadboard first. Now let's get into inLab08. So start with the website first because I included most of the inLab questions over here. So this will help you a lot tomorrow. We didn't finish it on Monday, so I was wrong on this diagram because I was doing the low pass filters frequency response, but this is the microphone's response. It's a different stuff. You don't remember what I talked about on Monday, so that's okay. All right, let's start from zero. Okay, start over. So this is the frequency response of the microphone. What does that mean? It shows the gain here, so it's not attenuating the signal until 20 kHz. It's an input signal. Okay, your voice getting received by this microphone, so it's not getting attenuated. Not getting attenuated with a really good range. So it's showing you that your voice, whatever, lower than 20 kHz is not getting attenuated. Okay? And what's the relationship between the input and output signal at 0 dB? Remember last time we talked about the transfer function? What does 0 dB mean? What is 0 dB? 0 decibels, but where is that? So 0 dB means what? So 20 log something, right? Which is 0 dB. So what is this saying? 1. Because 10 to the power of 0 is 1, right? Okay? So if this is 1, what does that mean? The gain is 1. V out over V in is 1. So it's not attenuating it. No attenuation. Okay? So that's why you are seeing 0 dB here. Okay? No attenuation. Microphone works perfectly. No problem. You are not expecting it's getting amplified, right? Because there's no amplifier in there. Okay? So what is the relation between the input and output at 0 dB though? Same. They're the same, right? Okay. What's the gain of the low pass filter? What's the gain of it? 1 million over 10K is 100. So the DC gain is 100. So if you draw the AC response, what's going to happen for the gain? I'm drawing the gain, input-output gain, okay? Including the DC gain. Keep in mind, because that's related to another question over here. But let's do this first. Just for this guy, okay? Oh, before we move to that DC gain. This thing, you see, microphone signal comes into here, and it's being put up to VCC, okay? The reason for that is the microphones is a it's called a lec29. How to pronounce it anyway? So it's a device that you don't have to part it up. It's going to directly generate charges. It's really interesting. So your voice is like a wave. It's going to hit that microphone, okay, like this, distort it, and eventually it's generating charges. However, the amount of charges is too low. That's why it requires that you have to put it up to VCC is providing it's a DC voltage. DC source is the AC ground. Have you heard about that? DC source is the AC ground. It's hard to imagine and why, right? But just remember that it's providing an AC ground over here. Whenever you got a resistor, the AC signal is getting dropped. So you are getting imagine this is the AC ground, drew a ground over here. If you got a bigger voltage, a bigger resistor, you are getting a bigger drop. So which means actually the AC is getting more gain over it. I know it's confusing, but so higher resistor will give you a higher AC voltage being lifted up to a certain level. So eventually, it's just a required circuit. If you look at this microphones diagram from the data sheet, it's required. See, you have to put it up to VCC. Just put it up. So in your circuit, when you are engaging a microphone for the project, just don't forget this resistor. Just put it up, and eventually this AC signal comes in. It's hitting this capacitor, which is a high pass filter. DC voltage will get removed, and AC signal will get through here, and this half of the range will lift it. It's like a DC common voltage will lift the signal. So AC signal like this, right? And that DC common voltage here is a 50% of the AC range, DC range, will lift it to half of the range. It's going to lift it here. So whenever you amplify it, it's going to be amplified like this. Okay, it's going to swing around the middle pin here, the middle range, instead of getting cut off at ground. So that's the whole purpose of that. But the AC signal arrives here, and here's the DC gain, which is 1 mega, 1 million over 10K, which is 100. So you're always getting that 100 DC gain. It's confusing, right? So here is a low pass filter, but however, the capacitor, for example, you're getting DC signal. The DC signal is not getting attenuated by this low pass filter because this capacitor is blocking that DC. Is that difficult to understand?
The DC only goes through the resistors.
DC only goes through the resistors. So the DC gain or the low pass or the low frequency gain is always what? 100. Okay. Whenever the frequency goes up, the capacitor got engaged, so it's attenuating the gain. And we already derived it. We derived it last time, so it's gonna perform like this. Okay. If you're curious about the corner frequency, refer to the notes from Monday. Okay? You need to know that for some of the inLab questions. So here, it's called FC. For example, this is 3.3 kHz. And what's the corner frequency? How this was calculated? It's 1 over 2 pi what? RC. So what is R and what is C here for this circuit? A lot of things you don't have to derive it all the time. After you did it once, you just remember it. So during the job interviews, you can answer this question immediately. Nobody is going to ask you to derive it all the time, right? When you are seeing this structure, it's the structure of this low-pass filter has been there for 100 years, pretty much. Maybe not 100, let's see. Who invented integrated circuits at the very first time? Jack Colby, I think, and who won the Nobel Prize in 1970s, and then started Intel. You know that, yeah. Right?
Yeah, I just Googled it.
Yeah. Okay. So this is the low-pass filter. It's going to be always look at this, similar to this kind of diagram. So if you see this in the job interview, you want to immediately tell them the corner frequency is just 1 over 2 pi RC. The R and C's are these two guys. You're curious about how these are getting derived, just refer back to the notes from Monday, okay? So R is what? 1 million ohms. C is what? 47 picofarads. Okay? This is one of the inLab questions. Okay? Do this. Find out the corner frequency. I think it's 3.3 kilohertz, if I remember this correctly. All right? And if you move by a decade on the ramp, if you move here by a decade, it's not changing anything. But if you move here to the higher frequency by 1 decade, which is 10 times the corner frequency, it's called a 1 decade in frequency analysis. Just 10 times more.
How do you spell that? Oh, that's the LED. 1 decade.
All right? How much attenuation you are getting here?
Minus 20 dB.
Minus 20 dB. I calculated last time. I don't want to do this again today. Don't have time. So make sure you know this, and make sure you know that at the beginning here is not 0 dB. Why? What is 0 dB? 1, right? 0 dB is 1. VO over VIN is 1. But however, for this case, it's not 0 dB. Refer to this note, it's important, okay? Because some of the, I found out the inLab solution, and I already shared the correct version with the TAs, but just in case they didn't receive it or something, they are telling you it's 0 dB. It's not. Because we have what?
The gain's 100.
The DC gain. So what's the DC gain is? 100. So 20 times 100 is what?
2000.
Oh, no. 20 times log 100. Sorry. It's 40, right? So what is here? 40 dB at the very beginning. Make sense? So the DC gain, why is called DC gain? The terms, DC gain. Use all these terms in the interview, okay? Why is it called DC gain?
The gain of the DC voltage.
The gain of the low frequency voltage. Very close, okay? Low frequency, no attenuation, because it's a low pass filter. Make sense? 40 dB. When it's more than the corner frequency starts attenuating. So what is this attenuation here though? How much drop from here to here? Why we don't directly use here? Why we want to use this one? Remember the whatever we derived last time? It's 1 plus this is the transfer function, right? So when F equals FC, you're getting a 1 here, and eventually this guy becomes 1 over square root of 2. And you do 20 times log of this, you're getting what? Negative 3 dB. So when F equals FC, you're getting what?
Negative 3 dB.
Negative 3 dB attenuation here. Yes, 37 dB. Perfect. This is called what? What is this called? The bandwidth. Or 3 dB bandwidth. Is that all clear? All right. Any question on this? How do we get this? Refer back to the Mendes notes. Don't have time. Yes, transfer function. Questions? No? Move forward. All right. Calculate the corner frequency of our LPF. What is it? It's one of the inLab questions. What is it? I'm just repeating. What is it? 1 over 2 pi RC. R and C. R and C, okay? Next, you apply a 1 volt peak-to-peak sine wave with a frequency of 30 kHz. Calculate the amplitude of output from the LPF. What is this? Corner frequency is this, okay? What is this? 33K. It's exactly the same frequency over here, right? It's just trying to use the ramp and minus 20 dB. However, it's assuming that this guy's, even though it's attenuating by 3 dB, but it's assuming it's not attenuating, okay? Which is okay, it's a very minor change. So this one is gonna attenuate it by 20 dB, right? Okay, so just do the subtraction. Just the subtraction. Okay, so for the ADC connection on the board, if you look at the schematic, it'll write a label as RA5. What does that mean? It's connected to the pin. It's connected to the pin, which is RA5. So the R is hard wired. It's physically wired on the PCB. You cannot change it. So what the reason for that is, if you look at the diagram, is this the table looks like the table I drew it or the Carlson drew it, or is from the data sheet? Yeah, data sheet. Now let's look at RA5. RA5 here. Okay, so RA5 inside the chip is actually connected to where? AN4. AN means analog. AN4 means the analog input channel number 4. So RA5, Dr. Carlson connect RA5 to connect the output of LPF to RA5. It's trying to inject the signal to where? To the ADC. Channel 4 of the ADC. Okay? So it's already physically shorted to the ADC's input. You just need to do the configurations, the MCC stuff in your MP lab, right? So to make it happen, because it's being multiplexed. RA5 could be used as GPL, could be used as something else as well. You just have to set it up in MCC to use that RA5 as an analog input pin. Okay? That's how that works.
Did you just jump RA5 to one of the LEDs and whistle and it would turn on?
No, I directly just probe it. Oh, LEDs, what do you mean?
Like if you jumped RA5 to like the R LED and you whistled, would it work?
The voltage is too low. I believe the brightness will be changed because this is getting amplified by 100 times, right?
Yeah.
Even though it's attenuating a little bit, but it's still being amplified. So because I probed it, I can see the sine wave in the oscilloscope. So I believe that voltage swing is right around like 1 volts. It should be able to turn on the LED because there's a DC offside. Let me draw it for you. Remember that that wave in the oscilloscope? So for example, here's the oscilloscope, okay? And 0 is over here actually, and my whistle was here. Okay? So the DC offside is already able to turn the LED on. So this will just adding some fluctuation to the brightness.
Gotcha.
It's gonna work. Okay? You're wondering, can this thing, can my whistle drive it? Is my whistle that powerful, generating enough charges to turn on the LED? So powerful?
Very.
Can I drive it? Can my like voice signal provide enough charges to drive that LED? It's getting amplified.
Yeah.
You are not the only person like contributing to the charges. Who else is also contributing?
The op-amp right there.
Op-amp, but where? Which part of the op-amp? The power supply, right? The power supply. It's gonna provide currents, charging and discharging. Okay? All right, so this table shows you all the connections, the pins, and you can see that you have more than like 10, 8 or 10 ADC channels.
Did you set up
You can
a
choose.
DC for-
It's a really powerful design. So the way you do that is it's just multiplex, right? So you have multiple ADC channels. You sample.
look at that.
Does it work? Yeah.
That's pretty cool.
Where's the power? Oh, you powered it up with just okay. Gotcha. Okay, cool.
That's pretty cool.
It started turned on and then it just went up and down with how much
Yeah.
the brightness.
If you have multiple channels, you just select this channel, sample, select another channel, sample. You do it very quickly, so you can eventually still sample like many analog input channels. Okay, in the future, probably in the senior projects, you'll have to use multiple ADC channels. So if you have like more than one analog sensors, do you need like more than one pick? No, just use more than one channels, right? Just multiplex it. You can buy a multiplexer that can input digital signals, so you can select from 000 from the 0 pin to like the 8th pin in a certain sequence. You can scan through it. So select each analog input to the ADC. But anyway, for here, it's just asking you to find out which pin is connected to which analog input. All right, it's another question in the inLab. And for here, I think the video demonstration that I showed in the video doesn't have, for the very first one, doesn't have ADC involved because I just directly probed over here. You can see he demonstrated that I can show the signal on the LED. Definitely can probe and show in the oscilloscope. Okay, no problem on that. This is what I did, and if you whistle too close to the microphone, it's gonna saturate it because the amplifier has like 100 times DC gain, right? Yeah. So the frequency of your whistle is what? Let me take a look. It's a good quiz question, right? What's the gain, overall gain of this AC signal? Let's see. Is that 10 hertz? Less than 10 hertz? Yes, less than 10 hertz. This is really low. It's not getting attenuated, right? Because still over here. 10 hertz is just over here. Still low frequency, so it's not getting attenuated. So that's why it's getting amplified by 100 times. You think your whistle is so loud, it's getting amplified. So when you move further away, that's, if you move further away, you're seeing a smaller signal. It's not getting cut off on the top or bottom. So you can use the AC coupling to remove the DC offset. So eventually you can move it, swing around the 0 point, the baseline, instead of having a large DC offset on the top. Okay, then get an ADC. Remember, when you are doing the ADC channel, you are opening up AN4. So that's the setup. Has to be done in the P mode and also in the ADC's setting here as well. See? Have to select AN4 to make it work. Okay? So it's a really simple inLab, and I'm gonna talk about part of the code. Let's get into here. That's the inLab code. So ADC is really simple stuff. Basically, it's just a sampling analog signals by doing this. Okay, here's a microphone. Your whistle comes in. Okay, samples points during a certain interval. Okay, that's what that does. And ADC, right? It's an analog to digital converter. So eventually, it samples this guy and will convert it into a digital signal. The digital signal will be multiple bits. And for the ADC we have, it has two registers called ADC. Can't remember it. I cannot remember it. ADC something. Don't want to give you wrong information here. ADR ESH ADRESL. Okay, so that's where you hold the PIC microcontroller holds the converted data. However, it's a 10-bit ADC. It's an 8-bit microcontroller. So eventually, these register banks are 8 bits. Okay, but you have 10 bits results. How do you store it? It's either justified to the left or to the right. No, it's either taking these 8 bits, 10 bits, or taking these. Here, or these 10 bits.
The second.
Oh, the second one. No, I mean you have an option. There's it's not a question. There's a little bit called ADFM. It's either 1 or 0, so you can select. You want to justify it to the left or to the right. Doesn't matter. So, however, if you look at the code, something you need to understand over here. Look at the code. Here, see? ADRESH. If I'm using these 10 bits, and if I'm so picky right? I just want exactly 10 bits. So what should you do? You have to grab these 2 bits and shift it to the lower two LSBs and OR it with this guy to find out the final 10 bits data, right? Okay? However, I think none of the code used it and it directly dropped these 2 bits. These 2 bits are dropped. Does that matter? Is it affecting anything? You see? It's so the data being converted. Again, lab is super simple. It's basically just the ADC will do the job inside the chip, and the data will be ready in this register. That's it. You just need to read it. So the most difficult part is what? MCC. It's always the most difficult part, right? Even though I provided all the code in the template, or sometimes I send the code through email to the students, still take like one or 2 days to figure out what's going on because the MCC setting is wrong. Anyway, so okay, I wish you can set it up correctly, and eventually you see, it's just super simple. It's the data is ready in there. Just read it. Just read it. So there's nothing else will read the lower 2 bits, but directly just using the upper 8 bits. It doesn't matter. So what this is affecting is what? The resolution. Why? Because whenever there's a tiny changes, it's flipping here. It's not getting sensed or getting reflected to the upper 8 bits. Who cares?
So we have 8-bit resolution instead of 10-bit?
Yes. Yeah. Yeah. Who cares? Your whistle. Your whistle too loud. Cares about like 2 lower LSBs. Nobody cares. Okay. I mean, for this project, we don't care. For some other projects, we may care about it, so you have to engage these 2 bits. But anyway, just let you know, it's only using the upper 8 bits. Okay. So how this is getting sampled using ISR. So for this kind of sampling, you want to keep it consistent. So sampling during certain intervals. Let's say this is 100 microseconds. How could you implement it?
Just figure out how many timer counts.
How many timer? Yeah, use a timer. And usually we just want an ISR to do the job. Okay? So make it really clean. So you just want to make your ISR interrupt for every what? Every 100 microseconds. Then you are done.
Why do we write to the timer twice?
Yeah, that's what I was thinking.
Yeah, because these are 2 options. I'm trying to ask you which one's better.
I see.
Which one's better though? Or which one's correct? It's not better or not. It's just correct or not. Take a look. So the sampling, let's, I know, just want other students to follow as well. So keep that in mind, okay? We are doing ISRs, so ISR interrupts every 100 microseconds and come into the ISR and sample it. Okay, that clear? That's it. Super simple. Comes in, sample it. Comes in, sample it. And it's sampling for 16 times for this inLab. Super simple code. Only come here for 16 times. So now, let's come to the ISR, see how it's getting sampled. So the testing pin set high, testing pin set low is trying to let you measure how long it takes to do the sampling. It's nothing else. It's nothing to do with the ADC. So for the ADC, it's just one line. You turn it on. This is a certain register. You turn it on, it's gonna start a conversion. Okay? You turn it on, boom. One thing is sampled and stored in the AD whatever SH register. Okay? Everything is done automatically inside. Just turn it on. I mean, do you need to turn it off by yourself? No, it's gonna turn it off by itself, by the pick. But not, you don't have to turn it off manually. You'll never see whatever here equals 0 anywhere. You don't have to do it. So turn it on, after the conversion is done, it's gonna be cleared by itself. Okay? So you know that after the conversion, after turn it on, the flag, so new sample will be ready. That's why you'll turn the flag on and then do the timer stuff. Okay? To control the ISR's time. Which one's correct, which one's not. So in the past, we don't have this one engaged. Why? Because we don't care about the precision. Now it matters. So we want to keep all the conversion exactly 100 microseconds. You are not doing some signal processing stuff. It's precise, very precise. Doesn't like playing music with speaker in lab 5, right? For undergraduates, it's like a toy. Now we are being serious. Okay, so timer 0 rate timer, which is whatever has happened after it gets into the ISR. So it's the time consumed by these lines. Okay, so when we are doing a timer counts, you want to consider this amount there as well. So my question is, whatever the count has been made by these lines, do you want to add it? Do you want to? Let me draw it for you. So here's the timer, right? Timer 1. Here's the start value. Which count determine the timer's time?
Time till it.
Here, right?
Yeah, so you want to take into account like how many
Okay.
seconds it's already taken.
So something else is also taking time. Do you want to subtract that from here or add it in here? How would you like to do it? You just put in here, right?
Yeah.
This is something wasted. It has to be considered. So you have to put in here. So eventually you are getting a shorter or wider number here.
You're getting a
Shorter, right?
Exactly.
Because someone already takes some time over there. You have only a little left. Make sense? So which one to use though? Which one to use?
So
Which one to use?
yeah,
Which one to use?
plus timer plus
First one or second one?
second.
Wait. Yeah, second one, right?
To add to how much you're taking away from the full bit to get the time that you want.
But if you remove the parentheses, it's minus this guy, which is the desired
That's what I
one,
was thinking.
and then plus this guy.
But the thing is that if you're adding to the retimer, then you're still making it shorter, because since you're doing minus, minus, plus, if you're the time you've taken in your ISR, you've like ticked up like let's say 100 counts, then you would be adding that to there, which would still be shortening it.
I think this is longer. Yeah.
Oh, that one is long. Yeah.
Yeah, because this is a bigger number here, right?
Yeah.
The bigger number will make this one move to the left after you subtract it.
No, because
No,
you
but-
want it to be exactly 190%.
Yeah.
But if you scrunch this down,
You're not
by
necessarily stretching
time
it down.
going down in the ISR, then you want to get it back to be the amount of counts that you want.
This is already consumed. It's already consumed.
Okay.
Yeah, you don't want to add it to there
So however
anymore.
much time is done in that.
Yeah.
So you wanna make- you wanna
still
make this
counted
shorter.
until you're using, yeah.
You want to make this shorter.
So it would be the
Oh,
first
because that time has been used.
Yeah, it's being used.
Okay.
because you're still whistling during that time, you know. So it would be the first one.
Yeah, anyway, so the discussion is recorded. If you are confused, you can always come back, right? But this is not being tested. I don't know in the future. Anyway,
Because if you subtract the amount of time that's been in there, then you add it to there, you take into account that you already written there, and then you can do 1600 minus that.
okay, so this is the answer, okay? All right, let me ask you a simple question. This is what we usually use.
Yeah.
This is the correct, the more precise version.
Yeah.
So, we should use this, not this, okay?
You're trying to be yeah.
ADFM, I just talked about it, that, which is a register you can choose. It's left justify or right justify. Okay, see? So that's the two registers. You either keep the data here or keep the data here, okay? So in our lab, we do ADFM to be 0, so we keep it to the left-hand side. And when you measure, for the first task, it's asking you to measure the interrupt, the sampling rate. Okay, it's asking you to use the function generator signal, be careful because the function generator can go over 0.3 volts. So probe it to itself, to the oscilloscope first. Make sure it's not overshooting. Okay? Keep that in mind because you know the channel's attenuation has to be 10x.
Yeah.
So make sure make sure it's 0.3 volts. It matches 10x on the probe, 10x on the scope, and you are reading something lower than 0.3 volts. So that one's getting put into there, and then eventually you are sampling, and you are getting something like, oh, I have it for you. Oh, here, right? See, I measured it. It's 103 microseconds. It's really accurate.
You want 100?
We want 100, but the thing is, you see the cursor has errors, right? So the signal is moving around, and 103 is really accurate because I cannot zoom in. The spikes are so narrow. If I zoom in on the time scale, the spikes are out of screen. So I can only do it this way, but eventually I'm not sure if it's exactly aligned with the rising edge. So eventually it's very close to 100 microseconds. The scope is not accurate, but I think the ADC is really accurate.
With have you seen like how long like the delta is when you don't do that? Like
132 microseconds.
132, gotcha.
So you did way better.
Way better.
Way better.
Yeah. I remember I had it, but why it's not here? I had a screenshot.
Yeah, I was just curious.
Anyway, so I showed it here somewhere else. Is that here? Anyway, so but the inLab asks you to do that, okay?
Yeah.
So you will be able to see. It's gonna be 30 microseconds difference. Huge difference. And for whistle, you do ADC, you follow the procedure shown in the demo video, and you'll be able to plot it. So there's no magic over there. Okay. So inLab now is covered, I believe, for most of the questions. There's something else I have to talk about for the lab, but I think we have the chance to do it on Friday. Okay? Any questions? All right. See you tomorrow.
Thank you, Professor Lee.
Yeah.